and the ratio between direct and diffuse radiation. Whereas the LAI-2000 uses 5 probe angles, and so using different probe angles, it's possible to obtain a LIFAR index measure without no other information. Okay, but the problem in this case is that okay, it's so difficult to have a sensor for direct and diffuse radiation in a smartphone. This is the first problem, and even the use of 5 probe angles means that the computation capacity of the device should be better than the one you have usually in the phone, because lookup tables are needed and so on, solving some complex equations. And so these 2 methods were not suitable to be implemented in a smartphone. But there is this Warren Wilson, which is a very nice guy. Nobody knows him, but he's a wonderful guy. For example, the equation used implemented in many models for crop growth. It's known for network synthesis based on radiation interception and radiation efficiency. Is known as the Monteith equation. You know the Monteith equation? Okay, Monteith just provided theoretical basis for that equation, but this is the man who really discovered that equation. And okay, make a lot of interesting things. And among these things, is developed a particular version of the light transmitter model, a very simple one, but very effective, which is based on just 1 probe angle, and this is the probe angle needed. So 57 degrees. If you use this to acquire the information, this angle, you don't need any information about the canopy structure. Then, a few years ago, Barrett and colleagues provided a theoretical demonstration of this evidence. So it's a simple model, but effective and can be used. And so this is where we start from. And this is the flow chart of the application, so you have an idea of how it works. First, you have to specify the code for the measurement, so the name of the plot, the date of what you want, the name of the fields, or I don't know what. Then you have to wait 5 seconds, because sometimes it's needed to put the device below the canopy. And then you have to rotate the device, okay, along its main axis, and automatically it acquires information at 57 degrees. And then the information, the image is acquired, it's processed, and then there is a visualization on the screen of the LIFAR index value you obtained. The data are also stored with latitude, longitude, the name of the plot, and what you want. And of course, this data can be exported currently in 2 ways: in a tabular format or in a shape file, so compatible with GIS. This is the version of the application we just supported. We are now supporting, but in the past we tested another solution which was not based on the processing of images, but on the luminance measured by the exposimeter, the digital exposimeter of the device above and below the canopy. So something similar to the ceptometer. This is the graphical user interface of the application, and I will try to briefly explain you how it works. There is a manual, settings, data table, and so on. So now let's imagine to have the application in your hand. This is the integrated quick manual, which is available in the application. You have the possibility of specifying some options. For example, you know that in that case, under those conditions, in order to get a representative measure, you have to perform 5 replicates. You can say here averaging. Average shoots, you click and you give the information of 5 replicates. So there are automatic statistics calculated by the device, and so on. And then the next step is to provide a name. Okay. In this way, parcel number 12. You know. And then after this, you get in the measuring mode. So you have to turn the telephone the horizontal way, and the next step is to select the proper sky conditions. You have to give the information to the application if the sky is full cloudy or is clear or mixed. And why you have to specify this? Because we implemented two segmentation strategies. So two algorithms for processing the images that are acquired at the desired angle. The first is for cloud sky. The segmentation in this case is based on pixel intensity. So the leaves under those conditions are darker than the sky. So this is used to estimate the gap fraction in your image. The other algorithm is when you have a clear sky or mixed sky. In this case, of course, it can happen that the radiation directly go into the vegetation, and so the vegetation could appear brighter than the sky. So no intensity can be used to discriminate among the sky and leaves pixels. And so the segmentation in this case is based on pixel probability values in an HSV color space. This one is okay. And then, of course, you have to turn the telephone, to rotate the telephone along its main axis, as shown here in the quick guide. And because we have seen that angles are so important for indirect methods, the probe angle is very important, and so probably bubble levels are not the best solution to have an accurate estimate of probe angles. So we use the accelerometer implemented, already available in the device, is available for games and so on, to derive an inclinometer. So we have a digital inclinometer which allows us to get the image automatically when the probe angle we would like to have as target has been reached by the device. Moreover, this is also important that images are acquired in live preview mode. So, live preview mode is the one you see when you have to take a picture of the device before clicking. You see, okay, and that is the live preview mode. This is because you see that here they demonstrated that this is the 57.5 angle, and if you deviate, if there is an uncertainty from this angle, the error in different index estimation can be relevant. And so if you say to the device, okay, rotate when the angle is that one, let's take the picture, according to the device you are using, take the picture could mean 1 second or even 2 seconds. And so if you are rotating the smartphone, and if you take 1 minute, 1 second after the correct angle is reached, maybe when the image is acquired, you are at 85 degrees. So in this case, in live preview mode, it's instantaneous. Okay? So processing, this is the equation we used, the Warren-Wilson model. This is the gap fraction. The first algorithm we tested when we started developing this application was the one of segmentation, and you see here, this is the picture, and this is the results of the processing of the picture. White is the, in this case, is the gap fraction. Then we also tested a method based on luminance, so using the device exposimeter. So basically, the gap fraction in this case is the ratio between the luminance below the canopy and the luminance above the canopy. And these are, okay, the focal ratio and something which is available as information provided by the exposimeter in most of the devices, not in the Android one at the moment. And okay, now this is the application. If you have further doubts, or I don't know, you want to know something more, then you can make the questions you want. At the moment, I would like to speak about some tests we performed. So the first test was the evaluation of the PocketLAI and other indirect methods, so the AccuPAR ceptometer and the LAI-2000 for rice by adapting the ISO protocol for the validation of analytical methods. Because it's possible to read many papers about everybody's testing these indirect methods against destructive method and so on. and someone report the R-square, someone else the mean square error, someone else I don't know, and the protocol used to collect the information to be compared is always different. So it's in different papers you see, okay, the ceptometer is the best one, the LAI-2000 is the best one, the hemispherical camera is wonderful, and so on. So we said, okay, let's try to standardize the way we use to validate these products. So for analytical methods, they made a lot of work to define standard protocol for the validation. And we try to adapt that protocol to our case. This is the first test we performed. And then last year, we performed another test by just comparing the PocketLAI with the ceptometer, the AccuPAR ceptometer, in conditions very challenging for the application. And then I will explain you why. And this is another paper with Impress. This is available with Impress. So the first test, the ISO protocol for the validation of analytical methods, define accuracy, because even when you read this paper on the validation of different tools, you always say accuracy, precision, and sometimes you don't know exactly the difference between these two terms, and maybe even the authors of the paper don't know exactly the difference between these two terms. So the people working on the validation of chemical analytical methods define accuracy as composed by trueness. So the trueness is this one. If you have, this is the true value, the reference value you have, it's 4. If you have a number of replicates like this, you say, oh, awful results. No, these are not awful, because the mean of the red values is exactly 4. So if you have the possibility of performing many replicates of your measurement, and the mean of your replicate is very close to the reference value you have, this means that the trueness of the methods is very good. Okay? This is a component of accuracy. The other component is precision. This is precision. This is the mean, this is the reference value. Yeah, it's okay. Okay? This is the reference value. Here you have the values of your replicates. You see that the mean is 6. So it's useless, this method. No, it's not useless. It's very precise. The trueness is very low, but it's very precise. Moreover, they define precision as composed by other two concepts, which is repeatability, which is the possibility of making, okay, I'm the user, these are the conditions, so the same condition, the same user, the same instrument, I replicate many times the measure, and the repeatability describes the variability among the methods, the replicates, the values of the replicates performed by me under this condition at the same time, using the same instrument, and so on. So this is the repeatability. And then there is the reproducibility that describes the variability, which is among replicates performed in different moments, by different persons, and so on. Okay? It's clear, this? Yeah. Okay. Usually, these studies are performed within interlaboratory tests that are also named as ring tests or ring trials. This means that many labs are involved in this validation. When in chemistry, when they have to validate a new method, many labs are involved in this process. So, different laboratories and different operators for each laboratory. This lead to estimate the reproducibility of the method. Why different laboratories? Because usually you give the protocol, the analytical protocol, and you say that, okay, let's perform the analysis on reference values. They start doing the analysis, and maybe there are differences in the interpretation of the protocols. And then we have different operators, because of course, if different operators apply the same method, there can be a certain variability. Then different levels for the analyte. They provide the reference values with different concentrations of the analyte, and this to understand if there is a good linearity in your method. Different replicates for each level, laboratory, and operator in order to get reproducibility and repeatability. Then, if you have reference materials, you can even calculate the trueness, which is the agreement between the average of all your replicates and the reference value. This is not so easy to be adapted, to be applied to field experiments, of course, to methods dealing with living entities, which are plants. So, how we adapted this protocol? Different laboratories, okay, I have a course at the university. I teach cropping systems, and there are students which are very interested in all these projects, parallel activities. And so we identified 4 groups of students, each composed of 4 students. So for us, the laboratory were the groups of students. We gave them the instruments and the protocol we defined for each instrument without, and they were, okay, for them it was not allowed to speak about the interpretation of the method and so on. So we, in a certain way, we reproduced the effect of the lab, of different labs. Then, different levels for the analytes. Of course, you can build and distribute plants, rice plants, with different index. Okay? So, for us, the different levels were obtained by different sowing densities, which have an effect on different index, and different moments during the crop cycle. This allowed us to explore a wide range of different index values, starting from values lower than 1 to values reaching 5, 6, and so on. Different replicates for each level, lab, and operator. We identified, because this is difficult, because we use 3 movements during the season. 4 laboratories, 4 students for each laboratory, different replicates for each student within each laboratory, and different instruments. Let's imagine all these people going around into the plot and, okay, destroying everything, basically. So we found this solution. We identified regions in the fields, very small regions, to have homogeneity among plants. Okay, this 4 by 4 meter plot is our plot, and it's very homogeneous, so we concentrated on this. And then we divided the plots in quadrants. So we said to the students, okay, let's work only here, and make your replicates for each laboratory and for each student, 1 here, 1 here, 1 here, 1 here, in order to avoid trampling effects. So we assumed these quadrants as homogeneous, because we selected a very homogeneous parts of the field. It was small, so it's possible that it's quite homogeneous. And so the replicates were performed in this way. So to avoid trampling effects, basically. For the presence of reference materials, okay, no true values are available for different index. And so we assumed as true values the values coming from the destructive method, which is the best you can do for different indexes if you want to have a reference value. So, first, for the interlaboratory test, first, in order to avoid that the effects of the operator affect, maybe there is one of the students who is not so enthusiastic with this work, and so, okay, let's do this measure. In this case, to avoid that this behavior affect the final values, first you have to detect outliers in your measurements. And so for each level, which in our case is different plots with different sowing density and different dates, for each laboratory you detect outliers on variances and on means. So the concurrent test has been applied to detect outliers on the variances, so the largest variance is due to the students like this, and the group test on the mean. After discarding outliers, this is the ISO protocol, we calculated the trueness on the remaining values. So some matrix, error matrix calculated, so the root mean square error, the modeling efficiency, the coefficient of residual mass, and the linearity, and so on. And then for the precision, we calculated the standard deviation of repeatability together with its limit, and the standard deviation of reproducibility together with its limit. Okay? And these are the results. For the trueness, this is the LIFRA index calculated with the destructive method, and this is the LIFRA index derived with indirect methods. You see that here, this is the one-to-one line. Oh, the main conclusion here is that the version of the app based on luminance above and below the canopy was the one, circle, was the one with the best trueness. Okay? Whereas the other instruments are pretty much the same in terms of trueness. Okay, this is good, and here there is a saturation effect, which is shared for all the tools we use. Whereas for repeatability, this is the for each date, for each sowing density, we calculated for each of the methods we used. So app G means the version of the app based on the segmentation of images. App L means the version of the app based on luminance. And 5R and 4R means that the LAI-2000 was used both in 4 rings configuration and in 5 rings configuration. Okay? And for each of these conditions, you have the limits of repeatability and reproducibility and the standard deviation, the relative standard deviation of these two values. The main conclusion here is that the version of the app based on the processing of the images is one of the most precise. Most precise means that the lower variability, there is a low variability among different replicates for the same user and for different users. Whereas the version of the app based on luminance has an awful precision. Very good trueness, but it was so sensitive to the way it was used by different students and so on, that at the end we decided to abandon this version. This version is not supported anymore at the moment. Okay, another result from this first test, this is the values of the different index measured with the destructive method, here and here. And here we have the repeatability limit, okay, and here the reproducibility limit. This means that no relationships here for the repeatability limit while increasing the values of different index by the destructive methods. This means that, okay, you can take the average of this value in order to say that, okay, I make the measure, and then, okay, different replicates, my replicates differ for, I don't know, 0.5 or 1 at the end, maximum range, okay, it's within the limit according to this validation. In this case, there is a linear, clear linear relationship between reproducibility limits and different index with the true values of different index. And so, for the version of the app based on luminance, this means that if you have, I don't know, like you go into the field and you measure 5, okay, you can use this equation to derive the reproducibility limits for 5. Of course, this is good because there is a linear relationship. The ISO said that this is good because if you have a line, you can calculate your limits for whatever values you are measuring. But of course, you see that the limits is 4 for different indexes. This is absolutely not reasonable. Okay, the second test we performed. This is the assumption behind each method for light transmitters into the canopy. You should have infinitely small leaves distributed in a random way within the canopy. This is what you should have in order to apply these indirect methods, which are all the methods implemented in tools like the ceptometer and so on have this assumption behind. Of course, for rice canopy, this is okay. They do not deviate so much from this assumption. Leaves are not so big, and the canopies after the first stages, canopies are reasonably homogeneous. Whereas other canopies are completely different. This is maize, this is giant wheat, and this is natural grassland. In this case, you have very big leaves, row seeded. So big leaves, not small, and no homogeneity at all. For giant wheat, okay, this is an incredible situation. Very difficult canopy to be analyzed, very challenging. And whereas in natural grassland, usually you have small leaves, but the canopies are not homogeneous. You see here, the big heterogeneity. And so we said, okay, let's try to understand if the model for light transmitters into the canopy we used, which is simpler than the one implemented in commercial tools, is suitable not only for rice, but for these challenging canopies. And so we performed this second test. So the three canopies markedly deviate from the assumption behind the light transmitters model. Maize had, of course, big leaves, it's row-seeded. Giant wheat, big leaves, in case it is grown for commercial purposes, for bioenergy. It's a row planted, plants are very far one from each other, and the plants has a marked tillering aptitude. Usually, they plant one plant each 2 meters, both in this direction and in this direction, and after 2 years, you have a completely closed canopy. Okay? Grassland, okay, not homogeneous, most of the cases. So in this case, no, we didn't apply the validation protocol before because it was very time consuming. And so we said, okay, let's try to compare the estimates provided by the application with those coming from the ceptometer, which is one of the most widespread tools. And for extensive field campaigns, it's considered, let's say, a reference because it's very quick to get measured. It's not among the methods, the tools available, it does not cost too much, and so on. So let's make a comparison. The measurement protocols was for the ceptometer, for maize, these are the raw maize, and this is the bar for the ceptometer. You know the ceptometer? Okay, good. This is the ceptometer. And this ceptometer. And this is the bar, this bar is the red. Okay? Whereas for giant reed and grassland, we performed 5 readings below the canopy, and we consider the average of these 5 readings as 1 replicate, and we performed 2 replicates. With the application, the smartphone application, we use for maize this protocol, okay, this maize, 5 measurements in this way to consider the trampling, the clamping effect due to the row. And 2 replicates, even in this case, and for giant reed and grassland, we use the same protocol as for the ceptometer. These are the results. So, for maize, the situation is not so bad. This ceptometer estimates, and this is the values provided by PocketLAI. You see that for giant reed, especially for giant reed, but even for maize, to an extent, there is an overestimation for low values of leaf-area index. Overestimation by assuming the ceptometer as a reference. Okay, we know that it's not a reference, but we assume that in this case. And this is due to the big leaves and to the clamping effect, rows, and very big leaves in this case. And then there is an overestimation here for values higher than 5, and this means that the model we used is more sensitive to the saturation effect, which characterizes all the indirect methods. Of course, under these conditions, with this kind of canopies, we really markedly deviate from the assumption behind the model we used. For the grassland, there is no systematic errors, but measures are more spread. You see here, very close to the one-to-one line, but more spread. And this is why there is a very huge heterogeneity, and the ceptometer has an 80 centimeter bar. So, part of the heterogeneity, which is in the canopy, is captured by the 80 centimeter bar. Whereas for the application, probably it's needed, not probably, it's needed to perform more replicates. Okay? Because the sensor is 1. In that case, I think that you have 8, 10 centimeters average sensors and so on. So, more replicates are needed by the, okay, it's something very close to the one-to-one line. With more replicates, probably the distribution of errors probably will become something like this. So we have the same one-to-one line, but with less spread values, let's say. So, some conclusions. PocketLAI results were comparable, at least for rice and wheat. So, small leaves, quite homogeneous canopy, are comparable according to our validation. to commercial tools for both trueness and precision. Okay? And we think that it represents a nice solution in contexts which are characterized by a low availability of resources. Because, okay, in order to make these comparisons, we need the ceptometer, and we bought the ceptometer, okay. We paid more in Italy, I don't know why, but 4,700 euros. And okay, but in some conditions, some contexts, probably this is too costly. And so this is for sure, the application of the smartphone is for sure cheaper. So in some contexts, this can be a nice advantage. And moreover, it's a nice solution when portability is a requisite. When you have to make very extensive campaign, you have to go around, and even if you are a car, I did it during these studies for testing the application. You have the car, you have the case, okay, you stop, you open the car, you open the case, you open everything, you take the measurement, you go inside, you close, then 200 meters, and you open the case, you open it, and so on. In that case, you have something in your PocketLAI. Or even in case you, when a number of instruments is needed, if you have to cover a wide area and you have just one device, because 5,000 euros are so much, you have 1,000 and you have to go and 2 days, 3 days to take the measurement. If you have a very cheap tool, cheap is the word, okay, very cheap tool, you can both, I don't know, 10, so to distribute the device to 10 persons, and so you can get the same measurements in 3 or 4 hours, probably, and not in many days. Remarks, because there are also some remarks. It presented a device effect. This is something not so good, especially for low-cost devices. We noticed that calibration of the segmentation algorithm is needed because of the quality of the camera, the quality of the sensor, and so on. And so, at the moment, maybe we will work together in the next months to optimize, let's say, in case of need, of course, the segmentation algorithms implemented in the application for some devices. Probably, maybe we will use in the future for these aims. And we will develop next year, probably, he will develop some automatic calibration routines, okay, to have the okay, in this case the device effect will not be a problem anymore. The method, one of the results we take with second test, the method is less robust than the ceptometer in case of canopies that markedly deviate from the assumption of random distribution of infinitely small leaves. But in case of rice, this is not a problem at all. And then, of course, we noticed in northern Italy, where we perform these tests, the sky is blue or it is cloudy. And so usually it's very easy to select the proper algorithm for a cloudy condition or clear sky. Whereas when we arrived here, Andy said, okay, let's go to the field with the ceptometer and demonstrate the camera and the application to make some comparisons. Okay, this should be clear. And it was not clear at all. And so then we switched to the other algorithm and the results were wonderful. So this means that, of course, there is a subjectivity in persons that are looking at the sky and say, maybe I'm optimistic. So it's clear. Maybe another person would say the same sky, it's not clear at all. And so we are developing, he will develop some routines, automatic routines to automatically decide which kind of sky you have, and so which kind of segmentation algorithm you should use. This will surely improve the user experience and, of course, reduce the impact of the subjectivity of the people who's looking at the sky. So, I almost finished. This is the application. This is the device with the application. If someone, maybe I will take a measure here. Let's say, okay, suggestion. which lies here. 5?
Maybe some question before.
No, then the question. This is part of the presentation. Okay, let's provide an estimate.
Who dares?
Anyone?
LAI estimate?
2.8. I will try. Of course, in this case, we don't have sky. It's not clear and it's not cloudy, but I will try to imagine that these are clouds. The color is not so different. And let's try to perform a measure. .53. So probably the estimation of 3 is more reasonable, but we are inside the building, okay, and it's not the sky and so on. But it's not so unreasonable, let's say. Okay? If you want this application, and you can try to use it. And okay, this is a small surprise, and you already know it. We are also developing pocket nitrogen. And this is secret results because we will send the paper next week, so nobody knows that. We compare the nitrogen concentration from the elementary analyzer measured in the lab for, okay, we do the same protocol for the validation we follow for LIFRA index. And these are 6 methods we compare. This is the SPAD. You know the SPAD, everybody knows the SPAD. This is the leaf color charts we developed here at Erie. This is the dark green color index, is an index they developed for greenness. And this is the corrected version of the same index, an improved version, whereas this is the dual X. Who knows the dual X? Nobody knows the dual X. But I also discovered this instrument last year. It's something like a SPAD. You go in the field and you make like this on the leaves. And okay, let's look at what the SPAD do and look at what the dual X do. The repeatability, you see that the variability among the mean is not so good as for the SPAD. So you need to take more measurement replicates using this dual X. But look at the trueness. This is incredible. Compared to the SPAD, this is based on not on the absorbance of light from the chlorophylls, but on the emission of fluorescence from the excited chlorophylls in specific bands. Not only the chlorophylls, but even the flavonoids are estimated. So flavonoids, secondary metabolism, chlorophyll first, primary metabolism, and the ratio between the two provides an index. And this is really incredible. And this is pocket nitrogen. You see that here, the trueness is very close to the one shown by the SPAD. Of course, not good as this one. Very close the trueness to the SPAD. Of course, the trueness is so good, but the variability among replicates is a bit larger. So the repeatability and the reproducibility, so the precision of pocket nitrogen is not good as the one of the SPAD, but the trueness is comparable according to our validation protocol. So this can be also in this case an alternative to the SPAD in case of no resources available. Coming soon. We have a prototype running, and next time we will present the application. So this is my team. Okay, the Pocket and the application Pocket. Okay, this is Simone. I can recognize probably Caterina. I don't know. Difficult to recognize from this picture. And okay, I think that's all. So thank you really very much for the attention.
Thank you, Roberto and Marco. As I mentioned, if you want to come and try after the question session, you can test the app. You can look at some of the other methods we've been using and compare how easy this is compared to the ceptometer and everything else. You mentioned going out with 10 phones as an example. We need to do it with hundreds. This is why this is so appealing for us. There's no way we could do 100 of these, not on our budget. and as you mentioned, they break, and it's expensive and it takes time. So we'll come and try. We have time for, I think, 5 or 10 minutes for questions. So, is anyone with questions for Roberto or Marco?
Yep.
I've created a weather API for every longitude and latitude.
Sorry?
I've created an API for weather for every longitude and latitude, current conditions using satellite data coming in. So it might be interesting to validate the person's guessing with the actual weather condition. And it's updated every 15 minutes, the API. So I wanted to give a business card to you. It might be as a correlation to what people's guesstimates might be, or something like that. I don't know, it's just a speculation.
Yeah. Thank you very much.
It's easy to embed and it's free and it's open, so you can just plug it straight in.
That's good.
I think
Thank you.
Lilia,
No, thank you very much.
Yes.
Interesting.
I was just wondering, can you tell us what type of phone this works on?
Okay. On Android phones, and I think that from the version 2.2, 2.3 to the more recent. So it's all the Android devices are okay. Sorry?
No iOS.
No iPhone, but everybody is asking for this iOS version. Maybe we will pay someone for translating the app for iPhone because everybody is asking this. We didn't care at the moment about the iPhone version because of course there is water, the paddy fields and so on. And so this is 250 euros. The one we use for the validation is 130 euros. Probably it's not so I don't know, good to go into the field with $700, $800, $900 device.
But is there, for the Android, is there any specific brand of phone that you thought worked better or?
Oh, okay, we discovered this device effect, so we are thinking about calibration of the algorithms. But at the moment, for the Samsung, we obtained wonderful results. But even with HTC
And LG.
and LG, whereas we had problems with Alcatel. You know Alcatel?
Yeah.
As a rule of thumb, don't buy the cheapest, but don't buy the most expensive. Because cheap model have a low quality camera, and as everything is based on image, if you have a poor sensor or more correctly poor lenses in front of the sensor, your picture isn't good enough. So stay around $300. Let's say something like that,
2 or 3, yeah.
2 or 3.
And try to avoid, I don't know.
It is useless to buy Samsung S4, for example. Why? Because it's they are introducing into these high-end devices some pre-processing features for giving you smart picture, very beautiful picture. As a developer, I cannot stop them. So my application is receiving a pre-processed, nice to see picture, but unsuitable, or well, some way degraded for the algorithm. And so remember, you are going to put that phone in water, so don't spend too much.
Yeah. Moreover, because maybe it will be possible to have some post-processing of the values you are obtaining, even with these, I don't know, 900 euros devices. But of course, you have to calibrate because of the device value. Then you have to post-process. And so each time you add an uncertainty, an amount of uncertainty in each of these steps. And so at the moment, it will be possible probably to modify in post-processing the values you obtain. And so to have an S4 working perfectly for different index estimation. But it's why you're spending so much time, money for S4. Yeah.
How much data are we talking about when you are taking pictures, how large are they? Are they transferred to some kind of cloud server, or are they staying in the phone? And how much power does it consume?
Roberto said we are using live preview. Live preview is not constant over all devices, but we saw that they are using for live preview VGA. Basic VGA means 740 pixel, 320. So very small pictures, the smallest. And because we realized there was no need to take a 12 megapixel picture and then apply the algorithm to this. It was not needed, simply not needed. And but the real reason is what Roberto told you before. When we started working with low-end, mid-range phones, there was the delay effect from telling the phone, we are at 57 degrees, shoot. As you can see the display when you are bended and you're rotating the phone, this means that on an old phone you are shooting at a random angle above. Of course, on a modern smartphone with quad-core processor, it is almost instantaneous. But we are aiming at something cheaper. And so we started with live preview, and we are still relying on just live preview. For the second question, yes, everything happens in the phone. So we are not relying on server processing. Every computation is made inside the smartphone. We are using a image processing library. That's why the application is not really small, but it's some 5-6 megabytes. It's not that big. And data is stored inside the phone. So you don't have to rely on any connection to have your data processed. It is almost instantaneous. On all device, you have the value processed in 2 seconds.
Less than 2 seconds.
Yeah. When you pull up the phone, you wait 2 seconds, you see the number appearing. As processing takes more on maybe 800 megahertz processor, while on 1.5 gigahertz it's.
Moreover, also the information. Okay, the tabular values are always storing the figures in the database. Whereas for the live preview mode images, there is the option of storing or not. If you don't store it, you can use it for I don't know, without needing anything in terms of storage on your device. But there is this option because sometimes for the calibration of the algorithm, it's useful to send us the images which are acquired, and then we calibrate the algorithms using that images. Okay.
One thing I just want to follow up on that. One thing we'd really like to do, we're working with this app, is in SSD and CESD and other divisions too, we're all developing apps and collecting information in the field. And LAI is one of the things we want to collect. We ask the farmer the yield, the variety, the fertilizer treatment area, and transfer that to a cloud or to a database. Our idea is just to do it over Wi-Fi, so the field technician would be collecting a number of samples, and whenever they go back to a Wi-Fi hotspot, it would automatically send as a batch. We thought about doing a SIM card. That's important. I think when you're in the field and you need live feedback, we're just taking information one way. So we can wait, get it into a database, and then it goes after. So that's what we'd like to do, integrate it with our surveys, GPS, camera, everything else, and LAI is one of the key things we need. What would that?
Last presentation actually I really enjoyed. As one thing, hopefully it is free application, but if it is not, then how much we have to pay for one application?
The point is that not really the software, but the methods behind the software, so the segmentation algorithms, everything related to the device has been, there is a patent of the University of Milan. So we are not the owner anymore of the app, and of course, they are trying to mainly they would like to have collaborations like the one I hope that we will have for I don't know, some hundreds of licenses to a certain institution, and then also support for the development, for supporting the calibration and so on. And for single persons, we still don't know how to do it because we are not the owner, and they are trying to understand which is the best solution for them. And but he is one. It's wonderful to tell the device, and there is one of the version. So, but in any case, since okay, there are the paper published, and there are a lot of people making the same question, and so I put in all of them in a mailing list, and when we will have the solution, when they will told us which is the solution, I will email all of you how to do it. Okay. Roland, and then.
I was intrigued by also the nitrogen component that you showed in the last slide, because while there are these interests in measuring the chlorophyll or the nitrogen, the real challenge I see it in terms of getting something to the farmer is putting a calibration to that in terms of amount of nitrogen.
You're right.
And the thing that strikes me is you have a very unique opportunity to put the two tools together. To put the leaf area and the nitrogen together into a calibration tool that could potentially integrate into some of the types of fertilizer recommendations that we're doing here.
Yeah, because you mean to integrate the two?
That's right.
Yeah.
What I mean is that when you take a leaf area, when you take a nitrogen tissue concentration of a plant at a given time, it's only meaningful in terms of the farmer if you can put it into a rate of fertilizer to apply, and that has some factor in terms of the plant performance.
Yeah, and this is another idea. This was the secret for the next year, but I will. If you have please something to write. Okay.
Remember, do we have any markers?
Oh, yes, here.
Okay. Oh, the one is enough. Okay.
It's right.
That's okay, that wasn't important.
No, because of course you know that. Okay, first we used calibration plots here, of course, because the index, spot units, and so on. And but at the end, even when you have, you know better than me. Okay, another one. Okay. You can have here something, I don't know, above-ground biomass, or time, or development stage, and for sure, if you can have here the nitrogen concentration, if you have here, I don't know, 2.5% of nitrogen on the biomass, this can be high or low. The plant can be well supplied with the nitrogen or not, and so usually in modeling activities, there are these curves that reproduce the critical nitrogen concentration in different, according to the development stage or according to above-ground biomass and so on. In this case, the critical means that if you are here, you know, probably, yeah, for sure you know, because I know you, your papers and so on. And you are here and the plant is not stressed. If you are here, the plant is stressed. So if you have here the measure coming from the dual-X or the leaf color charts, I don't know what, and you don't have this curve, you cannot say it, because in this case the plant is not stressed. But if the curve is this one, the plant is stressed. And okay, I developed with another 3 or 4 years ago with my students. We didn't develop an application, but a new method for the estimation of critical nitrogen concentration in for rice based on leaf area index. Because in most of the cases, you see that it is based on above-ground biomass, dilution curves from Salette and Lemaire, Just, and so on. And then some of the in Denmark and also in the United States, they used to reproduce these curves based on development stage. But the development stage is difficult to determine directly in the field in an accurate way. Even the biomass, you have to harvest the plants, to go in, put them in the oven, and then to dry, and then to wait, and so on. Whereas we develop a method based on leaf array index. So one of critical nitrogen concentration based on leaf array index. In this case, no more secret, no more labs in the future. So it will be really possible to go into the field to have an estimation of leaf array index, to have an estimation of nitrogen, and so to have this one. And when you have the critical nitrogen, there are some, I don't know, critical nitrogen multiplied by 1.4, you obtain the maximum nitrogen concentration in the plant. And so with this information, the maximum and the point where you are, you can try to estimate, according to the target yields you are trying to reach, the amount of nitrogen to be distributed, 40 kilograms or 45 kilograms, and so on. And so using the leaf array index as a driving variable, as a driving variable for these critical nitrogen concentration curves, you can go directly to the field and obtain them. There's no oven needed, no harvesting plants needed.
Yeah, I think this is really important because there are many groups out there that are interested in leaf color right now, but the reason that their approaches are so limited in terms of what we're doing is that it doesn't really translate into what's really important to the farmer, and that's putting it into a rate of fertilizer to actually apply. And I think you're onto something here that's really unique by putting the two together in terms of at a given time to take a measurement of the crop and translate that into a fertilizer amount, tie it into something like the rice crop manager, where a farmer already has an amount of fertilizer recommended, and then you can modify that up or down based on this and send it to the farmer as a text message, because we will already have a record of the farmer. So I think something that maybe is the next visit to Erie.
I'm looking at the time and I see we've overrun already quite a bit. So maybe if you have questions, you can ask one-to-one. If you want to have a demo, you can play with the plants and see how it goes. But thank you very much for a great seminar. Thank you for your attention.